and it can't just be based on the outcome, right? Or sorry, it can't just be based on some properties of the weights, right? And people have tried to make different versions that do this. We also don't want to make a metric that's dependent on the outcome. That's actually really important. And we also don't want a metric that is that is based on data points that are close to the decision boundary. We want to use every data point in our training set to construct this generalization measure, right? More importantly, we want to just be able to compute it from training data, because if we try to use test data or we try to monitor the model in production, why? So they created a metric, and what they did is they conceived this thing called the margin distribution, and it starts by defining a decision boundary, right, for each class within the training data. And they wanted to try to make a boundary that has a maximum margin. So what they did was they created a function that minimizes the distance to the decision boundary, and they attempted to approximate it, right? So you take this function and you create a Taylor series, and you get this function defined in equation 3 right here. And what it is you take the output at each level of the model and you divide it by the difference between the gradients at each level, right? Now, I went through and I computed it in code, and there's various ways of doing it. The way they did it was they went through, so they computed each gradient, right? And I'm trying to remember how it happened in code, so bear with me for a little bit. All right, so you take the first order Taylor approximation, and then you calculate it with each layer. All right, so you
have the code to show us?
I actually do.
Yeah, let's see it.
Oh, I mean, it's a little bit later.
No.
I mean, do you guys want to see?
Spoilers, sure.
What's the punchline?
What's the question?
What's I and J?
Oh, I and J. So I and J, that is the function that defines each class.
The two classes, I and J, different two classes.
Yeah. All right, so I'm going to show you kind of some implementations a little bit later. Cool. But I kind of continue. All right. So one thing to bear in mind is that when you create this distribution, it can be scaled by each layer. So if you have a constant that is in each layer, and then it gets pushed through, the weights, it can kind of get pulled out. So you want to normalize, and the way you normalize is you take the average of every function, you subtract it, and then you take the trace. All right. So once we've scaled, we essentially get this normalized. Now, the important thing about this distribution is when deep learning models are more likely to generalize, the distribution will be wider. So you can kind of see that right here. So here's a model that performs very well on the test accuracy. And you notice that the distribution for each layer is going to be really a lot thicker. And what you can think about is similar to the support vector machine, right? The boundary layer is going to be really, really far from the edges of your training points, right? Whereas if you have a model that doesn't perform very well on your test data, then your distribution is going to be really, really thin. And you can see that in the top, and you can see it down here in the bottom. And the more important thing is that you can look at the distribution for each layer. And I think that's actually really, really important. I'm going to point something out about this property. And that is that when you're constructing these architectures, you can actually kind of degrade different parts of the model. And you can see how different layers effectively are going to be generalizing versus other layers. And I thought that was really cool. That's amazing insight. I haven't really seen any other metric that goes really far into looking at the inside of every model. The more important thing, I think, is that you can, okay, so this is actually really important. By looking at statistical properties of the margin distribution, such as the average or the average or like the different quintiles of each distribution, and also the standard deviation, you can, so if you take, say, a large number of models, right, and each one of them has a margin distribution that will give you a different metric, that will roughly correlate to just how well they perform on the test set. And this performs really well against, versus other metrics. So this metric on the right comes from another paper that was computed earlier that only looked at the output. And you can see there's a much worse relation here. This one looks at the margin distribution. It's essentially basically a straight line. So there's a very strong correlation with the margin distribution and the performance of the model, whereas with other metrics, the correlation is just not as good. All right, so when I looked at this paper, I asked myself, well, is this just it? I mean, did they solve it? And the unfortunate answer is no. So in order to properly work through this, you need to have an entire set of models. You have to create margin distributions for all of them, and then you have to fit each distribution to their performance on the test data, right? This only really works with similar architectures, and it's not the exact thing as having a tight generalization bound on, for literally any kind of model. That being said, this is a massive improvement from just kind of not really knowing. Now, and you can still use it for trying to characterize your model. So this paper did a really cool thing where they use weight decay on different parts of the model. So if you're familiar with how models are constructed, you have a head of the model, and then you have so this thing called the pre-logit layer. That's the portion at the end. And by decaying weights in the head, and looking at the margin distribution in the head versus essentially the end layer, they kind of showed that while the performance might be similar, the contribution of the different portions of the model will change. And that is kind of what you would expect. You would expect that if you make it harder for essentially the initial part of the model to learn, well, then that part's going to be more like the generalized. Where if you make it harder for the end of the model to learn, then your head's going to generalize. So again, as you are constructing your models, you can look at different distributions and you can kind of see the inside. They made their own generalization bounds, and I asked about this, and I'm like, I mean, did anything become this research? And not really. They kind of just ended it. But okay. Yeah, so the code for it is available. You can kind of go in and you can look at how they constructed this they constructed this measure. I actually use this when I was building my own code. About right here is where they talk about margin distributions. So I think Banjo, you asked, how does this code work? All right, so sorry, this mouse doesn't work. All right, so here is where we have our here's where we have the numerator from equation 3. Can I do that? What you can see is they all right, so they capture the gradients through gradient tape. They put every layer into its own dictionary. So when they run an example through the dictionary, they capture it. Sorry, they capture it and they put it into the numerator. And then my favorite part is with TensorFlow, you can actually look into how gradients are calculated as they run through the model. They grab the gradients right here through the use of gradient tape. They slice it based off of the different labels and indices for each training point. They construct a norm, and then at the end, they divide the numerator by said norm, right? So that's TensorFlow. So the question I wanted to ask is, can you do this in PyTorch? Because PyTorch is really awesome. So I made my own version of the code that essentially does the same thing. I went through and I characterized each one of their models and actually computed everything exactly, which was very time consuming. I was actually in a cafe, like doing vectors with my hand. Now, the big difference is that when you're trying to get intermediate values with TensorFlow, you just look into the model. You can actually just get the layers from the model, and it works pretty intuitively. PyTorch, not so simple. You actually have to create a hook function that runs once the data points go through the model. This is similar to the other portion of the code where again I construct the numerator from the true values and the opposing values. And then finally, similar to how they used gradient tape, in Torch you have to actually use autograd, which took a lot of work to try to get right. And what this will do, this will give you the same expression as the other piece of code, and from that you can get the margin distribution. All right, so why was I really interested in working with PyTorch? All right, so a note about PyTorch. PyTorch and TensorFlow are not designed to work with one another. They're very different. They have different philosophies. TensorFlow, you grab your gradients through gradient tape. PyTorch, you use autograd. But the nice part about PyTorch is that if you ever go on like papers with code, literally every architecture is made in PyTorch. So it's much more Pythonic. It's much more easy integration with Lightning, which is a code base that tries to do things in production. So again, I kind of took it as a challenge to myself. Could I convert it into PyTorch? And I'm like kind of there. I was able to construct an unnormalized margin distribution on an MNIST model, which they did not do. And I was also able to replicate their results, at least for one model. When I say replicate the results, I actually went and I compared the outputs, and I compared all the gradients, and I computed I computed the margin distribution for for almost exactly. Now I have like my own roadmap The next goal for me is to completely replicate the results in this paper, to be more robust to architectures, which I kind of already am. So this model that I created the distribution for was one that I just kind of like made up in order to train on the MNIST set, right? It wasn't one that they used in their research. And then also to extend to other measures. So I kind of have this pipe dream of hopefully releasing it as its own thing, and like everybody can play around with it. All right, so there's been a lot of research on generalization, like a lot. Those two papers were just like literally a drop in the bucket. I kind of wanted to highlight some other papers that I think are really worth going for. So this one, which is called Large Margin Deep Networks for Classification, that is actually where they got the original idea for this margin distribution from. So in that paper, it contains the full-on derivation for it. The next one, which very funny named, Fantastic Generalization Measures and Where to Find Them, that does a more theoretical, essentially, that goes more into the theoretical fundamentals of how you do generalization, and it proposes different generalization measures. Which is funny because there was a rebuttal paper called Fantastic Generalization Measures Are Nowhere to Be Found, which was kind of a buzzkill. They basically said that this paper is wrong, so you can go read both of them and see which one is right, which one you agree with. That one wasn't as pessimistic, but still, it is kind of a I don't know, a contest. And then finally, which since everybody's into LLM, this most recent one where they actually look into the generalization of prompt engineering in large language models. So I skimmed over this one kind of recently, and what I essentially found is they made the case that it's pretty easy to predict generalization when you're trying to create prompts, which I have a lot of questions about that.
Interesting.
But hey, maybe there's something there worth doing. All right, so yeah, so that's it. Thank you for watching.
Thank you for great presentation.
Oh, thanks.
If you could rewind to a few slides back on where you had those different graphs with different distributions.
Yeah.
Yeah, somewhere here. So, okay, so we have this measure.
Yeah.
My just questions in general. How can we want to the right then the one to
Okay,
the left?
so
Like,
I kind of
how can
blocked-
we actually use it? You know?
Okay, so I kind of glossed over this. So what they did is they created 300 models. Each one of these 300 models, they would have different lengths, they'd have different widths, they'd have different numbers of parameters. Some of them would use batch normalization, some of them would use weight decay. So they essentially regularized each model, but despite them regularizing each model, they all fit the training data. The accuracies were like really, really high. So the general trend is when your model is going to be more powerful, you're going to get something like this on the left. When your model, less powerful, right? So if it's a shallow model that has really strong weight decay, then it won't perform as well in your test data, even though it might perform well in the training data. Whereas if it's a much more robust model, it's going to perform well in your test data.
I mean, like, what I'm trying to ask, like, my question is, okay, we have this indicator. It's just an indicator, right? It's
Yeah.
not an actionable thing. I'm asking, do you have any idea about any actions we can take to, like, if we train a new model, like, how can we make sure that, like, it's somewhere on the
How can you make sure that it's more on the test? Yeah, so I mean the general trend is you kind of similar to what I did before, you just give it more parameters, you allow it to perform better. But that is kind of an open question. Yeah.
Thank you.
I guess one question is, using this generalization method, how does this kind of relate to explainability? So by understanding this, can we understand?
Oh, that's a really interesting question, right? That's a really interesting question. All right, so explainability I find really fascinating because while it would be hard to create like an intuitive explainability, do you ever not random forests but decision trees? right? How like where you create a tree based off of different properties of your data, and each leaf on the tree creates a decision. So in deep learning, you have so many different parameters. It's really hard to correlate them to anything that's human readable. So I don't know if you can do that. But what you can do is since we can introspect into different portions of our model, we can kind of see to what extent are they contributing to its ability to generalize. So that's kind of the best that I can think of. If you're making different assumptions about how you're constructing your architectures, I think that could also help. Yeah.
Right. To be honest, I'm not really able to follow everything, but trying to make some obvious. So the first method you mentioned, it was like you're doing things layer by layer, right?
Yeah.
And by regularization, do you mean you kind of did some confinement to weights and bias?
Can you say that louder?
Like by regularization?
Yeah.
Do you mean like you put some like confinement to the weights and bias?
Yes.
And then for those, you need to get certain thing called margin, and that has to be done layer by layer, right?
Yeah.
And for that, I suppose, because it's doing the training, so you need the slope to get weights and bias to move to some direction.
Yes.
Basic gradient. And my question is, how more expensive is that compared to something as simple as you just like if you put a penalty in a cost function.
Yeah.
For example, like weights square, maybe like weights after value or like to the power 2.
Are you talking about like when you regularize with the cost function or
those are,
L2
like, very
regularization?
simple way, like you don't really cost much computational wise.
Yeah.
Because it seems to me when you do the layer by layer.
Oh, wait, so you're asking about how, like, what's the computational cost of computing the margin distribution?
It looks to me like very expensive.
It is very expensive.
Especially when you bring out the PyTorch and TensorFlow.
Yeah.
And even have the next question is, so I know TensorFlow is already there, and you're trying to
Yeah.
generalize to PyTorch.
Right.
Have you ever compared like the performance?
I actually did when I was constructing it. All right, so when I was making the PyTorch version,
Yeah.
the performance was a lot lower. It took me like, I think about 5 times.
Yeah. I had like bad experience.
Yeah, because what you're doing, okay, so what you're doing when you're creating the margin distribution is you're running through every training data point. You're computing the gradients, and then you're computing a metric on top of the gradients.
Wow.
And yeah, there's a lot of
So it's a loop over. So it's a loop over training data.
yeah, it's loop over training data, which is very larger than your
Layers.
test set. Yeah. What'd you say?
So it's a loop over training data and also layers.
Yes. Yes, it's basically you're computing the.
That's
Now I want to point out that since so much can be done with matrix operations, you can offload it to the GPU. Some of the challenge, however, is if you've ever worked with TensorFlow or PyTorch, you have to be careful of controlling what's on the GPU and what's on the CPU, what's
Like,
moving
you
consistently.
don't want to talk too much. Yeah.
Yeah. So that's part of the engineering challenge.
Thanks, man.
Was the effect that big, or was the difference in performance that big between PyTorch and?
Yeah, again, when I was making that PyTorch, essentially the PyTorch implementation, I was just kind of going quick and dirty. I didn't really do optimization.
Yeah, I was gonna mention the one thing that could explain that might be TensorFlow is much more optimized because everything happens in the graph in their computation graph, I think.
Mm-hmm.
And then if you interject in there, you're in Python land, and then things become slow, and like there's all these.
Yeah, I kind of got that feeling.
All these translations that go on.
Yeah, I think
So
this
you're not,
is
like you're putting yourself into its fast operations that even like theoretically it could compile, right? But like then you're inserting yourself with Python, and then things could slow down.
So one thing I noticed with PyTorch is that when you're constructing a model, I see you kind of choose if it's on the GPU or the CPU, right? With PyTorch versus with TensorFlow, it kind of, unless I don't know, depending on if you're doing eager execution or not, it's kind of like all on the GPU. So Yeah, I think that might be one of the issues. I might be passing data from system memory via memory, so that's one thing I have a plan to go back and check. But my primary concern was trying to get everything as accurate as possible.
How does this generalize to like different model architectures and like, I don't know, if you had like skip layers or something, like would that impact the architecture?
So that was an important thing. That was an important thing is that typically if only you're looking at the end, then it doesn't. But since as long as you can gain access to the values that are inside your model, and as long as you can gain access to your gradients, which you should have, right? Every architecture has that, then you should be able to construct this measure.
Focusing on sort of on the end there, and specifically that, how do you think this relates to, not the, I mean the end of the model, sorry, not the end of the application. How do you think this relates to like self-supervised and that like I guess self-supervised training and specifically, max, like selecting the margin? Because I think it's a really similar problem space, right? Sorry. Just the idea that, in self-supervised, you're really looking to, when you pick a point, whether or not you're going to classify or not as 0 or 1, right? How you select that, I feel is largely a function of where it sits on that margin, or whether you actually decide to classify it or move it to later in the system.
So when you're referring to self-supervised, are you referring to how
I'm
the
saying
model
we pretend that the model is, we have really have 1,000 trading points, but we start with 100, we train 100, and then we give it 50 more, and we say where do they fall? And I'm just curious where.
That's actually an interesting question, which maybe we could research ourselves. So the answer is I don't know, but that definitely seems like something that'd be really cool to attempt to address. Yeah. So save that question and I don't know, ask it on the Slack and maybe we can like live or something.
I was curious about you're running this on your local machine or using the cloud, or like how long does it take?
Oh, right on this machine.
Okay.
Yeah, I impulse bought this. I have massive insomnia, so I impulse buy a lot of things at night.
Yeah, so back to the previous question, people asked, and the question I asked earlier. So yeah, it seems like, so you have this indicator of like how good the model is, how it will generalize in the end.
Yeah.
So what previous people were trying to ask, and what was my question as well, can we like, flip it from the, so basically we do the training pass, then we collect the gradients, and in each layer we calculate this metric.
Yeah.
Right?
Yeah.
Is there a way to like basically do like, reverse the process once again? So we
To,
have
like,
this
use it
metric,
to
and we
analyze your
know
architecture.
that it's a bad metric.
Yeah.
And we know that, okay, in order for it to be like good, whatever it means, we need to do some changes to the gradient and like, basically do some optimizations so that the model we train, it will like, it will be like generalized right away.
Yeah. So I will point you to something, which is in the paper that precluded this one, which is large margin deep networks for classification. I feel like they did something like that. So what they did was they constructed a loss function which attempts to maximize the margin. And by maximizing the margin, they maximized its way of generalizations. Is that what you're kind of searching for?
Yeah, it does make sense. Yeah, so any thoughts on that? Like how feasible it is? Like,
I mean, it's already been done, so it is feasible. The question is, to what extent can you apply that to new architectures?
Should I like apply tomorrow in production or what?
So I actually will say sometimes what I've seen is okay. So I have this thing about deep learning research, which is that every one of these papers does the same thing. They say, oh, we did a technique. Here's some benchmark. We did the best on the benchmark. But every paper is the best on every benchmark. It's very weird. It's like, how do you know who's the right one? They're all the best. So the general trend I found is you just kind of have to experiment. I definitely think if you can implement something yourself or on your own data, then I highly encourage you to do and try it. But it helps if you can experiment really quickly.
Maybe last question.
So there is an answer to how do you know which is the best one. There's a site called Papers with Code /SOTA. Find it there.
Yeah.
That was a really quick one. Maybe one more question. I saw one more hand over.
Pretty well.
So you mentioned that this technique worked really well in some model families.
Yeah.
Do you know which model families they are?
So it was essentially okay, so the one that I practiced on, that was so they're using the CFAR10 data set. It was just a simple feed-forward convolutional network. I think so. It was a convolutional network with a linear layer, with 2 linear layers. Yeah, and they essentially just varied the number of convolutions, they varied the number of linear layers. Yeah.
Right, thanks.
Awesome.
Does that same margin distribution also apply to a transformers architecture? We can talk about this.
God, I would love if it did.
Question.
Theoretically, there's a deep learning portion to transform.
There you go, you got it.
It's their fault.
All right, cool. Awesome. Thank you, Elliott. Continue the conversation. We got a few minutes right here, but then we get kicked out. So go
Okay.
across the street if you want to keep talking.
How do I?
Way to rock.